We'll finish up this chapter with a couple more topics. The next one is kinetic molecular theory. The simplest model for the behavior of gases is kinetic molecular theory. In this theory, a gas is just a collection of particles, and those could be either molecules or atoms, and they're in constant motion. So we're still talking about ideal gases. We assume that the size of the gas molecules is negligibly small, and the average kinetic energy of a particle is proportional to its temperature in kelvins. The collision of one particle with another is completely elastic, and the same with the walls of the container. So kinetic molecular theory says that the particles of the gas are constantly moving. The attraction between those particles is negligible, and when the moving gas particles hit one another, the gas particles or the container, they don't stick, but they bounce off with elastic collisions. We also assume there's a lot of empty space between the gas particles compared to the size of the particles themselves. In other words, the size of the particles is negligible. All right? So the average kinetic energy of the gas particles is directly proportional then to the Kelvin temperature. So as you raise the temperature of the gas, the average speed increases. But that doesn't mean that all the gas particles are moving at the same rate. It's just talking about the average speed. The collision of one particle with another, or the container, is completely elastic. This means that when two particles collide, they may exchange energy, but there's no overall loss of energy in the system. Any kinetic energy lost by one particle is completely gained by the other. So here's what an elastic collision looks like. When two particles bounce into each other, they go off in different directions with the same energy that they had before. Maybe not the same by each, but the total energy would be the same. An inelastic collision would lose some of that energy to, say, heat or sound or other energy factors. So we assume that they are all elastic. Now pressure is given as force over area, and that's what keeps, let's say, a balloon inflated, is the pressure of the gas particles on the walls of the container. Boyle's law states that the volume of a gas is inversely proportional to its pressure, so decreasing the volume forces the molecules into a smaller space. More molecules will collide with the container, and that increases the pressure. Charles's law states that the volume of a gas is directly proportional to the temperature. According to molecular theory, when we increase the temperature, the average speed and thus the kinetic energy of the particles also increases. So the greater volume spreads the collisions out over a greater surface area, so the pressure is unchanged. Avogadro's law states that the volume of a gas is directly proportional to the number of gas molecules. Increasing the number of gas molecules causes more of them to hit the walls at the same time. To keep the pressure constant, the volume must then increase. Dalton's law states that the total pressure of a gas mixture is the sum of the partial pressures. According to kinetic molecular theory, the particles have negligible size and they do not interact. Particles of different masses have the same average kinetic energy at a given temperature. Because the average kinetic energy is the same, the total pressure of the collisions is the same. The kinetic molecular theory is a quantitative model that implies that PV equals nRT. The pressure on the wall of a container occupied by particles in constant motion is the total force on the wall divided by the area of the wall. So only particles within the volume defined by this area are capable of hitting the end wall within that time period T. So we can also look at kinetic energy as it relates to mass and velocity. And we can derive an equation that says that the root mean square velocity is equal to the square root of 3RT over the molar mass of the gas. So in other words, the velocity is inversely proportional to the molar mass at a specific temperature. How does the approximate root mean square velocity of neon compare to that of krypton at the same temperature? So let's look at neon and krypton on the periodic table. Neon is here and krypton is here. So what does this equation tell us about the velocity? It's inversely proportional to the molar mass. So neon is approximately twice that of krypton. Here we can see molecular speed versus molar mass at the same temperature. Oxygen is going to have a lower velocity than, say, hydrogen because at a specific temperature because it is heavier. But the average is going to be lower, but realize that not all gases, not all molecules, individual molecules, are traveling at the same speed. Some of them will be going faster, and some will be going slower. But the average velocity for the lighter gas is greater. All right? So we can calculate the root mean square velocity by the molar mass. We already saw that. And we can also use Avogadro's number to times the mass to give us some a little bit different calculation. I don't think we're actually doing this one, so I'm going to just stick with the previous equation. As the temperature of a gas sample increases, the velocity distribution shifts toward higher velocity. So you can see here molecular velocity versus number of molecules with the indicated velocity. As the temperature increases, the average velocity increases, but also it spreads out. Okay, so this results in a lot of molecules going a lot higher and more going a lot slower. So even though our average increases, we have a broader, more spread out distribution function. Which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size, and that all gas samples are at the same temperature. Which one has the greatest pressure? Well, this is kind of a trick question. So what they're really saying is which one of these boxes has more gas molecules, right? The one with the more gas molecules is going to have the greater pressure. All right, molecules in a gas travel in straight lines until they collide with another molecule or the container. The average distance a molecule travels between collisions is called the mean free path. The mean free path decreases as the pressure increases because there will be less distance between particles. Now let's talk about diffusion and effusion. The process of a collection of molecules spreading out from a high to a low concentration is called diffusion. So in other words, if you, for example, if you release, let's say, a perfume atomizer into a room, all right, the perfume molecule spreading out into the room is called diffusion. But effusion is different. The process by which a collection of molecules escapes through a small hole into a vacuum is called effusion. So we wouldn't normally see this in the natural world. The rates of diffusion and effusion of a gas are both related to its RMS velocity. So for gases at the same temperature, that means that the rate of gas movement is inversely proportional to the square root of the molar mass. So gases escape from a container into a vacuum through a small hole is called effusion. So that rate is related to the molar mass of the gas. So the rate, if you have a collection of two gases, the rate of gas A to gas B, the rate of effusion of gas A to gas B, is equal to the square root of the molar mass of B to A. And we do some calculations with that in our examples. So the rate of the effusion of gas A to gas B is equal to the square root of the molar mass of B to A. A glass tube contains an equal number of moles of helium and argon. After 5 minutes, half of the particles escape through a small hole in the glass. What are the relative amounts of helium and argon in the tube at 5 minutes? The tube contains a greater number of moles of argon than helium. Okay? Well, that's because, let's go back to our equation here. The rate is going to be dependent on the molar mass of those substances, and the one with the smaller molar mass is going to travel faster. So there'll be more of the heavier one left in the tube. Now let's talk about real gases versus ideal gases.